Hi, this is Christian Ramos, and this is my Physics 2 Lab 5. So, a little table of contents. So, we're going to have first the introduction, then the experiment, then the glow script code, and then lastly the analysis. The introduction, which the purpose of the lab is to collect data from real-life experiment and use computational model to more fully understand Faraday's law in action. Some of the concepts, so we have Faraday's law, which is both there in text, and then on the right, the Biot-Savart law, which is also there on the right, and then Ohm's law, which is equal to voltage is equal to current times resistance, then Newton's second and third laws, and then the results for our experiment. We have that the experimental trial, it took 0.85 seconds to go for the magnet to go down the tube, and then in glow script it took 1.189 seconds for the magnet to go down the tube. And finding our system and surroundings. System is the aluminum tube and the magnet, and then the surroundings is just everything else. So the experiment, the length of our tube was 0.305 meters, the inner diameter was 0.025 meters, the width was 0.006 meters of the aluminum, so the total width is 0.031 meters. So what did we do? We just dropped the bar magnet down the tube, we recorded the time from the top to the bottom, and then we repeated that 5 times. So you see all 5 trials here on the right, and then our average time was 0.56 seconds to get down the tube. So glow script 1, as you can see on top, we have our length, our width, our inner radius, and then our full radius. That is the initial conditions of the tube, and then we have our magnetic field function followed by our magnetic flux function. And then we have our induced current function, as you can see on top there. And then we have our magnetic force calculations for each ring. So we split it up into several different rings, and then we calculated each one. That's how we calculated the total magnetic force. Then we have the net force equation, which is the force of gravity plus the force due to the magnetic force, and that is equal to the net force. And then lastly, we have our simulation, and then we found that we had a value of mu to be around 4.5, and this does like accurately show what happened in the tube. So as you can see, the velocity time graph, we have a very rapid decrease in velocity, increase in speed, and then it evens out towards the middle time, and then right at the end, it goes down once more. This is due to the gravitational force taking over at the end of the tube, and then in the middle of the tube when the velocity is constant, the gravitational force is equal to the magnetic force, so that's why we have no acceleration and a constant velocity. So our analysis, the intensity of the coloring on the tube indicates the magnitude of current flowing through each ring. Red and blue indicate current flowing in opposite directions. Which color corresponds to clockwise current as viewed from above, and which counterclockwise? How can you know this? So answer to that, red is counterclockwise, blue is clockwise, and we know this because of Lenz's law. What happens to the dynamics of the system when you flip the magnet around? Pretty much nothing. It'll just fall down just the same, and it'll still have the magnetic force applied to it. How does the total time in tube of your real-world system compare to the total of your computational system? How might the computational system be made more accurate? One, they're already pretty comparable. And then how can you make it more accurate? One, by adding more rings, making it more accurate to real life, or by recalculating the magnetic dipole moment for this one specific magnet. And then what does the shape of the velocity time graph tell you about the forces acting on the bar magnet? Like I said before, for the areas near the ends of the tube, gravitational force is greater, hence the decrease in velocity, but increase in speed. But while the magnet is inside the tube, the gravitational force and the magnetic force are equal. That's why you have a constant velocity because there is no net force. And our second part of the analysis, what if the resistivity of the conductor were reduced as close as possible to zero? How could the dynamics of the falling magnet change? And this, then the induced current would grow to be very large. This is due to Ohm's law. As a result, the magnet would take even more time to fall down the tube. And then another question, what if holes or slots were cut into the tube? How would this affect the rings and currents of your model? There would be less rings in the tube, therefore less magnetic force. As a result, the time for the magnet to fall down the tube would decrease.